Hello. So today we'll talk about SVM kernels. Suppose we have a data set. Here we can see the four samples, the blue ones of one class and these red ones of another class. We don't have a linear separation boundary visible here. Maybe we could draw this kind of boundary, okay, which is not a linear boundary. Now, suppose we change these. How do we do this? We project all these samples to another dimension, that this is 1D data. Now we make it into 2D. So the one goes here, this one goes here, and so on. Now you can see that the blue ones are all on the upper half of the diagram and the red ones are here. So we can see this separation boundary, and we can also find this two blue ones on the upper boundary and the red ones here, the support vectors of this class and of this class. So that means a transformation of data could actually find a linear boundary where in the actual data we couldn't see it. Meanwhile, we would want to recall the dual Lagrangian objective function using which we had solved for the alphas, and using them we found the W and the B. Okay, that was how we had found our hyperplane. Now, in this, we see that the inner product of the samples of vectors features in. So here we could plug in some transformed version of these x's. Suppose we find a transformation phi of the x, then instead of the inner product of xi and xj, we could plug in phi xi, phi xj. So this another advantage of this dual formulation can be seen here, that it allows us to plug in any transformation of the vectors. We have this opportunity to transform our data into high dimensions and simply plug in place of xi, xj. So how do we do this? Consider a basis that consists of a polynomial of degree 2, everything up to degree 2. So what would it have? It would have the constant 1 and x1 to xd, because we are assuming a d-dimensional x vector. So the x1 to xd, then the squares, because we are talking of degree 2. So everything of degree 0, degree 1, squares, and the products of pairs. So this will make approximately these many elements in phi x. The transformed version of x, phi x, would contain these many elements if we were transforming it to a polynomial basis of degree 2. For degree 3, for degree d equal to 3 of this vector, we can, for degree 2, we have written these many, and for degree 3, we are enumerating the phi x vector. For one feature x1, we could write phi x in this one. So we are seeing how we could do the transformations and get the corresponding phi x vector. Now, some concerns come in, because this phi x has d squared by 2 elements approximately, and we have seen in our optimization objective that we are finding the dot product of the pairs. So which means we must do it for the dot product of the transformations, and this is for all pairs of samples. This is going to be very computationally heavy, and if we take a polynomial of degree greater than s, then your complexity further increases. So this is where we come to what is known as the kernel trick. What is it? First, let us see the dot product phi x dot phi y. We are writing this as this product, summation and the product. However, there is a very simple form in which this dot product can be enumerated. Since we are talking of polynomial basis 2, then the product is 1 plus x dot y. Now see, this is x and y. We are not talking of phi x or phi y. So x and y are still in degree d, not y, sorry. X is still in degree d. Okay. Yes, of course, this y we have used it here for a pair of, we would be using it for the sample. So we are finding this product in the D space, okay, rather than in the higher transformed space. So the product 1 plus x dot y square is in the original space, so it requires only D multiplication. So this part of the algorithm is reduced from order D squared to order D. The same thing will be holding if we transform the data to any polynomial basis of degree s. Okay, so we remain in the original dimension space. So we have removed the problem of computing the dot products of extended basis vectors, which was very expensive. We saw d squared by 2 elements in phi x and multiplying with another vector of the same size and n into n number of times, n squared. So this we are replacing with the computation of the kernel matrix, also known as the gram matrix K, which comprises of dot matrix of the original vectors, which are still in the D space. So suppose we have our transformation matrix from dimension Rd to Rm, and we want this phi x dot phi z or phi x transpose into phi z to get the inner product. Let us define a kernel function kxz equal to this dot product. Idea is that we might be able to compute this kernel function without actually working in the basis function space Rm, but rather in the Rd space. Okay, so that is our ultimate aim, that we are doing the computations at a lower dimension space. For example, we saw that for polynomial, kernel function is 1 plus x dot z degree, power s for integers s greater than equal to 2. We have seen this example for s equal to 2 in the previous slide. So what is this? This is what we are doing. So this corresponds to computing the inner product with a basis function that makes use of all terms up to degree s. That was the when we talk of this phi x into phi y and transformed into polynomial of basis s. The polynomial kernel function, this one, does this by computing the inner product in lower dimensional space, that is x dot y, and adding 1 to the scalar and then raising it to the power s. The implicit basis is of course growing in s. Okay, so what have we done? Instead of taking the computations to a higher degree s, we are doing the computations in our low dimension degree d. The matrix K of elements K, the pairs of elements, is the gram matrix or the kernel matrix. So that was the big advantage of talking of the kernel functions, because they are keeping our computations simple, however, still finding a linearly separable space, which is the purpose of the SVM classifier. So some popular basis functions, the polynomial basis function defined as kxy equal to 1 plus x dot y raised to the power s, sigmoid basis functions where the tan h alpha x dot y into delta, where alpha and delta are the parameters, and the radial basis functions where again this sigma is the parameter. So this was a little talk about the kernel functions and how they are useful in doing our computations in a low dimensional space, even though at the same time finding a linearly separable space so that the SVM can be used to find the decision boundary. That's all for today. Thank you. Thanks for watching.